All right, here um, we try to explore a little bit more how each the area elements um, internally works. This is partially, I think, a finite element software, and we use a quadrilateral element which has a four edge, which actually create on one area. But we often use also triangular elements, right? But ETABS, usually you'll see that this triangular element is not really the kind of meant to be kind of works in our vertical wall analysis. So let's see. So what I try to show you one more time, since I measured 100 feet tall, the wall, as like a 1 by 10, so that the whole panel of the wall has an aspect ratio 1 to 1, right? But instead of that, I just mesh it horizontally. It creates the 10 panel, but it's actually is 1 by 100, right? Because it is 10 feet, this is 100. If I divide by 10 here, so this is each one is 1 feet, but 100 feet tall. The the last one, I think, instead of using quadrilateral, the square or rectangular, instead I'll use like a triangular element, right? But it has the same wall properties. We have a same the point load here. So you'll see that what's actually difference. So first of all, I'm gonna just show you vertical deflections. Okay. So vertical deflection, even self-rate deflection, you'll see that we're see that because of this shape, right? And then how can I show? Okay, animate it. So you see, mostly self-rate deflection is vertical, absolutely vertical deflections. Yeah, shrinking, right? But since we have some triangular related mesh, somehow it works slightly different. Because of this, I think you could see that also checking the vertical component due to the self-rate might be the not equal. So here, every wall has the same reaction, but ah, this is true. Same reaction, 75, 75, but somehow internal the vertical stiffness causing something weird deformation shape due to the self-weight, which I see some. You know what? I think this is very minor, very small number extraction, but somehow exaggerated. So I think everything is, yeah, UX is almost zero, but this is relatively a little bit bigger, relatively, but it's so small enough, so doesn't really but I think gradually is something weird. But here is one thing that you could with double check is due to the wind load, right? Let's come on. Okay, and check the deflection. So I think the third one is what we expecting perform much close to our bending behavior. The second one is aspect ratio 1 to 10 has an issue. I think fourth one has also issue. Totally wrong. Give us a total wrong. Is but as steep as almost second one. But the last one is you can see that stiffness is much stronger. So it gave us the deflection 2.1, right? So you see that something sensitivity, and you need to understand each the panel, the area element. I think ETABS usually prefer recommend to use this quadrilateral for like rectangular elements, but with kind of aspect ratio less than maybe 1 to 2 or even 1 to 4, right? Maybe, but not 1 to 10. Obviously, it depends on that primary the behavior you are expecting. If this is totally bending behavior, but it actually aspect ratio really influence that. So some of them actually give us the wrong answer. Okay, so this is kind of good exercise. We need to understand this is, I think, the finite element analysis, advanced structural analysis courses should address and introduce the basic of finite element analysis and software. I think you might be heard that stiffness matrix class as well. So this is usually those classes cover it, but I tried to show you since you already struggle to find the right method how to create the model for cantilever wall deflection check. Okay.